Hi everyone, my name is Andrew Mo, and today I'll be going over my Physics 2212 Lab 2 results. So the goal of this lab is to basically produce a computational model of two charged tapes exerting an electric field on each other such that the charges on the tape are distributed evenly across the length of the tape. We'll use this model to estimate the amount of charge on each tape necessary to float one above the other. The purpose of this lab is to understand how to use superposition to calculate the net charge on an evenly distributed surface. The results of this lab are that the electric charge obtained with 100 segments is 1.82 times 10 to the negative 3 newtons per coulomb. So there are basically three fundamental concepts that are applicable to this lab. The first is Coulomb's law, which basically states that, which basically allows us to quantify the electric force that exists between two stationary charged particles. The second is Newton's second and third laws of motion. And the third is superposition, which basically allows us to calculate the net electric charge by summing up all individual electric charges, electric fields, sorry. There are basically two assumptions that were made before starting this lab. The first is that each U-tape that we made had about the same amount of charge evenly distributed across along the length of the tape. And the second is that there's zero air resistance in our system. There are basically two expectations that I had coming into the lab. The first is that the tapes will repel each other due to their similar charge state. And the second is that the tapes will float indefinitely if no other forces act on it. And so this slide basically shows you how to create the model. We've basically first created the U-tape by quickly pulling the tape off of a base tape, and we tested the charge of the tape by observing the interaction between it and our hands and a negatively charged pen and etc. And basically determined that the U-tapes are positively charged. We then constructed two charged tapes and observed their interaction by first placing a U-tape on top of two objects of equal height such that the tape is suspended like a bridge, and placing a second U-tape below the suspended U-tape until it starts floating. And so the results of our experiment are as shown. The tape length was measured at 0.189 meters. The tape's mass was measured at 0.00019 kilograms. The distance between the tapes was 0.03 meters. And the gravitational force magnitude was calculated by multiplying the mass with the gravitational constant, which we got as 1.85 times 10 to the negative 3 newtons. The electric force magnitude is equal to the gravitational force magnitude by Newton's third law, and we got that is also 1.85 times 10 to the negative 3 newtons. The charge on the tape was calculated with the electric field formula, which we got as 1.59 times 10 to the negative 8 coulombs. And so using those data measurements, we created our computational model in the Glowscript program. We first created a top tape, which was positioned at 0.030, and the bottom tape was placed at the origin. And using these two tapes, we basically calculated the net electric field from one of the tapes to the other by creating 100 segments and calculating the electric field of each segment and summing them all together using the principle of superposition. And as a result, this was our Glowscript model. And we got that the magnitude of the electric force was, again, 1.8262 times 10 to the negative 3. And the magnitude of the gravitational force was 1.8639 times 10 to the negative 3. And so in conclusion, well, okay, so I'll talk about the errors first. So basically, after doing this lab, there are basically two potential sources of error that could have arisen in this lab. The first is human error from taking the measurements, and the second is the assumptions that were made. And as a result, the lab summary and conclusion is that we basically were able to use the physics principles delineated in the first few slides to calculate the charge and use superposition to find the total electric field of a distributed surface. We were able to use Coulomb's law and Newton's second and third laws to help us find the charge of the tapes. And we basically used the principles of electric field and superposition to help us find the total electric field of a distributed surface. And the results basically align closely with my initial expectations. And so here are the answers to some of the lab questions. The first question was if what if you had modeled each of your tapes as a single point charge, like in the previous lab? And I answered that by basically saying that if we had modeled each of the tapes as a single point charge, we would have obtained an electric field of 9.9 times 10 to the negative 9 Newton per Coulomb, nearly half the estimated value of the line charge model. And basically, these elements differ because the point charge model only takes into consideration the y components of the relative position vectors, while the line charge model takes into consideration both the x and y components of the relative position vectors across the surface of the tape. And I said that the line charge model is more likely to be the real value because it most closely models the real world electrical interaction between the two charge tapes.